So your CoCO Midterm Exam 1 is tomorrow, and it's going to be during class time. So it is supposed to start at 8 o'clock, 8 a.m. Eastern Time and end at 10:05 a.m. Eastern Time. And today I thought I would give you guys some information about the logistics for the exam. What are you allowed to have during the exam? And answer some questions that you guys have already started asking in the chat box. So let's start talking about the logistics first. The exam time is going to be from 8 a.m. to 9:45 a.m. Eastern Time. So this is written as a 1 hour 45 minute exam. So let me write it like this. You will be expected to write your name on each page, and you also will be expected to index each page that you submit with a page number so that it is easy for us to track down what you submitted, how many pages was it. It will help with the grading. So please make sure that on each page you submit, you write your name and page number. I'm going to request that you have your own pages. Please do not write the exam question paper as the page because I'm not going to leave enough space on the exam. So please have your own paper to use. The exact same thing that you do for a homework, for example. The remaining class time, that is 9:45 to 10:05 a.m., that's 20 minutes. We are going to use that for scanning the exam and uploading the exam to Gradescope. So I want you guys to give yourself enough time so that you don't panic and you have the 20-minute time slot to upload your exams on Gradescope. Please upload all the pages, and as you do in your homework, map pages to problem numbers. After the submission, please go back and check whether the submission went through okay or not. This will help you and us for grading purposes. I don't want you guys to later realize that you accidentally missed a page or something. I want you guys, so that responsibility falls on your shoulders. During that 20-minute time, you are expected to scan, upload, and also check whether that submission was submitted properly on Gradescope. Just as the homework submissions, Gradescope submission for midterm exam 1 will automatically close at 10:05 a.m. Eastern. What is allowed during the exam? During the exam, you will be allowed to have a Boolean algebra properties page. This is uploaded on Piazza. It is under resources section. I created another subsection called midterm 1 resources. So that particular page you can have during the exam. Let me just take a moment here. Are you guys able to see the screen, or is it stuck? For some reason, it just kicked me out. So as part of the logistics, continued logistics for the exam, you will be required to join our regular WebEx meeting at 7:45 a.m. This is a little bit earlier than the class time, which is 8 a.m. And we'll use the first 15 minutes to get set up. With the proctoring, make sure that everybody has the Boolean algebra properties page ready, a non-communicating calculator, and their writing supplies. And as soon as it is 8 a.m. Eastern time, you can start taking the exam. Please write your exam on pieces of paper, just as you would for a homework. Make sure you write clearly, legibly, because you are going to scan it and upload it so that we can grade those exams. During the exam, you will be expected to keep your camera and microphone on the entire time. However, your computer volume should be turned off. So each of you will not be able to hear anything on the WebEx channel meeting, but I will be able to hear and see you guys. During the exam, if you have any questions, please type those as a private questions to me in the chat box. How would you know whether your computer volume is turned off? So I'm sure you have a mute button on your keyboard, right? I would just press that exactly the same way as you would mute your computer. So your speakers, or the way you are able to hear me right now, that should be turned off. However, your mic, the thing that takes your speech input, that should be remaining on. Yes, Alex is exactly right. I mean, output volume should be turned off, input volume should not be turned off. All right. Let's move on here. These are the Boolean algebra properties that you are allowed to access during the exam. This has been uploaded on Piazza under resources, under midterm 1 resources. So for those of you who have access to a printer, please print it out and have it ready during the exam. For those of you who do not have a printer, please write these specific properties by hand on a piece of paper and have it accessible during the exam. This is the only piece of information you will have access to during the exam. Boolean algebra properties page. All right. Now, in terms of specific topics for midterm 1, I have uploaded a document called midterm 1 topics on Piazza, and this is the exact copy of that. Our midterm 1 is going to be broken down into 4 major topics. The first one being number systems, and this includes integer as well as fixed point fractions. You should expect questions on each of these topics. I'm going to highlight things that are absolutely for sure going to be there on the exam. Base conversions, you should expect a question on base conversions. Absolutely, for sure they will be there on the exam. How do you convert from any base to any other base for both integer and fixed point representations, for signed and unsigned numbers? So you should expect base conversions. Base conversions, note that base conversions are not just limited to the 4 most popular bases, which is binary, decimal, hexadecimal, and octal. Base conversions, as you guys have done in homework 1, and you guys have seen that base conversions can be from base 4 to base 3, base 7 to base 11. So all those base conversions, there will be a question on that. There's no doubt in my mind. How do you represent unsigned binary numbers? How do you represent signed binary numbers using the 2 representation schemes that we have learned, sign magnitude and 2's complement? How do you do binary arithmetic? Specifically, we have learned addition and subtraction in sign magnitude and in 2's complement form. What are the advantages? How do you know whether there is overflow or not? How do you know specifically whether what is the range of numbers you can represent using n bits in signed the 2's complement form? So for example, over here I can write signed binary representations I can write range, I can write overflow. How do you check for overflow? How do you know what is the range of numbers you can represent? And all of this is for sign magnitude and 2's complement form. Then how do you do binary arithmetic? How do you add these signed numbers? Rules are different for sign magnitude and for 2's complement. 2's complement, you do not need a subtractor. Subtraction is represented as pseudo addition. So all these skills will be tested. And then, of course, we have the binary codes for decimal numbers. Those included what? 1 out of 10 code, 2421 code, BCD code. So all these will be there. So I would encourage you guys to go back to homework 1 and homework 2. Look at the solutions that are posted on Piazza. Make sure that you know exactly how to solve all those homework problems, because those skills will be tested for sure in the exam. Next, moving on to digital circuits. We looked at how do you implement logic functions using CMOS transistors. We looked at almost all the logic functions. Started with a buffer, then we went to a NOT gate, then we went to a NAND, we made into AND. We started with NOR, we made it into OR. So all those fall under the category of 2A, expressing logic functions using CMOS transistors. The concept of what goes in the pull down network, what goes in the pull up network. I encourage you guys to look at the last problem on the back exam that I gave. The back exam I'm referring to is the spring 2019 back exam. There was a question about given a CMOS transistor circuit, can you write the Boolean expression for that? So I would encourage you guys to take a look at that and see whether you are able to solve such problems. Next topic was logic expression to CMOS transistor circuit and vice versa. Are you able to go from a logic expression to a CMOS transistor circuit and from a CMOS transistor circuit back to the logic expression? So 2A and B are both related, and I would point you to the last problem on spring 2019 exam. That was the back exam that was posted. I also posted the solutions for the back exams so that you can verify your work, and you should verify your work. And if you have not worked on the back exams yet, I would strongly recommend that you use today to practice those problems. I'm referring to the spring 2019 exam because that is comprehensive coverage of the topics. The next topic was noise margin. If you know certain thresholds of inputs and outputs, can you calculate the noise margin in circuits? Let me highlight B here, because that is, according to me, you should expect a problem there. Next, the topic of noise margin. We talked about what are the consequences of connecting one gate to the other and having the output voltage change due to noise at the output of a gate, and what is the consequence of that at the input side. Obviously, if due to noise the output voltage changes, the input to the following gate is going to change, and it might represent the logic level incorrectly, or it might go into the undefined region. So you should take care of those thresholds, and you should evaluate the noise margin separately for the low level and the high level. So there were homework problems given for this. I would encourage you guys to take a look at that. Now, topic 3, Boolean algebra, properties and proofs, logic expression simplification. These are all you should expect problems on these. I will be spending some time during this review session doing some example problems for 3D and 3E based on student request. So stay tuned for that. How do you convert to NAND only synthesis, and how do you convert to NOR only synthesis, and so on. All right. Over here, logic, expression, simplification, and verification. These will be expected, you will be expected to use Boolean algebra properties explicitly. I will mention that in the question. Use Boolean algebra properties. However, you could use K-maps as a validation step. So you could do the simplification using Boolean algebra, lay out all your steps, step-by-step approach. You should show your complete work. But that work has to be using Boolean algebra properties. However, once you're done with Boolean algebra property, you're satisfied with the simplest form, you can quickly check your work by using K-maps. So you can only use K-maps as a means to check your work, but you should show your work of Boolean algebra properties. Step by step. Okay, various forms of representation. I'll spend some time about 3C as well, about what are the various forms and how you can go from one to the other. D and E is essentially converting a logic function to NAND only and NOR only synthesis, and we can do that because NAND and NOR are universal gates. All right, at this point, let me see what the question is. Why is the solution, let's see, why is solution? There's a question which I'm not able to read. Why is the solution written in terms of Cmos for last question on spring 19? Yes. So actually, let me do this. Let me also spend some time doing that. Where is that? Right. So I will spend some time addressing the spring 2019 problem as well. So stay tuned for that. I will go over that problem as well. All right. The last major topic here is of K-maps. So combinational logic synthesis, a very systematic approach to simplifying logic expressions using Karnaugh maps. And you should definitely expect, actually do this. If you are able to do a 5-variable K-maps, which has don't care conditions, then you will be able to do the 4-variable, 2-variable, 3-variable, all of that. So spend your time practicing the 5-variable K-map, and if you are able to do that very well, then you don't even have to worry too much about the smaller sized K-maps. And then the last one is how do you minimize for SOP and how do you minimize for POS, specifically pointing towards whether are you combining ones in the K-map or are you combining the zeros in the K-maps? Are you writing the groups as product terms or are you writing the groups as sum terms? So we talked about a lot of examples in the previous lecture, and I would encourage you guys to take a look at that as well. All right. So that's as far as topics are concerned. I've highlighted the ones that I feel are really important, and you should definitely expect questions on that. I'm not saying that the others will not appear during the exam, but these are the ones that the ones that I highlighted. You should focus more on those ones. All right, let's see. Okay. So this is about the CMOS. I will do that later. Now, coming to the logic function representations. We talked about this during our last lecture, but I have this slide up here as well. And this was the result of essentially me polling the students about how could you express a particular logic function. And we came up with 9 ideas. One was the logic expression, which could be in the form of a sum of product or a product of sum, or in the canonical sum of products or canonical product of sum. So are you able to take a logic function and express it in one of these 4 forms? Are you able to express logic functions in the form of a truth table? Are you able to express it using a logic diagram, which uses symbols of logic gates and then wires to interconnect them? Are you able to sketch up a CMOS transistor based circuit to represent logic function? And we'll say an example of that in just a bit. Are you able to write statements? If this happens, then that happens. So those kind of statements will essentially convey the logic for that function. Item number 5 and item number 7 are more or less the same. 7 is essentially statements. So saying out in words what the logic function should do. When 2 switches are on, the light switches off. So those are statements, but they represent logic. Underlying logic can be expressed in any one of these 9 forms. Item 6, Venn diagrams. So we used Venn diagrams and it worked very well because they are binary in nature. So shade and not shade. And we use that in our Boolean algebra properties proofs. And some of this was on the back exam. So, that's another way to represent logic function. The next one was timing diagram, where we looked at an example of starting off with a logic function, and then for some arbitrarily chosen input timing waveforms, be able to sketch the output. This is also on the back exam. This is the problem 11, I suppose. So take a look at that. Problem 11, spring 19. That has timing diagrams related question. And then of course you can use K-maps to represent logic. So if you can use truth tables to express logic function, you can obviously make that into a grid and express it using K-maps. All right, so why am I laying out all of these things here? Because you should be able to go from any to any, right? So make sure that you are questioning yourself. Am I able to go from 8 to 2, 5 to 6, 9 to 1? So you should be able to go from any to any. And once you do that, you know that all of these forms of representation, you are very comfortable in them. Okay, let's move on here. So there was a question related to NAND only synthesis and NOR only synthesis. So what I'll do is this. So first I'll start with NAND only synthesis. And I like to start simple. So what I'll do is I will start with a simple sum of product logic network. So let's see, I will draw a logic diagram which looks like this. Say I have AND gate here, AND gate here, going into OR. This guy has say 3 inputs, this guy has 2 inputs. So suppose the question was to convert this into NAND only. How would you do it? Well, if you notice all of these, level 1, what do you have? and this is level 2. In level 1, you have AND gate here, and you have AND gate here, and OR gate in level 2. So this is why I said this is a sum of products representation. So the two AND gates can be converted to NAND, and the step that I have to do is this. Let me use a pink to represent that. I have to add a bubble in the front here. And I cannot just add one bubble, I have to draw another bubble to cancel it out. And similarly, I draw a bubble here and I cancel it out. And then I notice that this is already NAND. This is already NAND. And this can be redrawn as NAND. Why can I do that? I can do that because of De Morgan's law. So I started out with a SOP, logic function. And I'm calling it SOP because first I do the products, the ANDs in level 1, and then I do the OR in level 2. So when I do that, and the question is convert to NAND only, that job is very simple for me because all I have to do is add the bubbles at the output of AND gates and add the bubbles to the input of the OR gate, and they convert to NAND only very, very quickly. Now, just so that I complete this discussion, let us suppose that this was a little bit different. Let's suppose the question was this. Let's suppose the question was that. So right now you have a not in front of the, after A. So it's A, not, and B and C. So how are you going to do this? Similar process. Add the bubbles in front, in here. This has become NAND. This has become NAND. This has become NAND. And then you represent a not as a NAND in which both the inputs are tied together. We have learnt this, we have proved that this is the same using Boolean algebra properties in lecture. So we have also done this guy. So I hope that now you can use this skill to convert an SOP function to NAND only in a very straightforward manner. Now, let us switch this around and let us say that we have a slightly different question. Let us start with the same diagram. I'm going to go back to my original one here. And I'm going to say the question is NOR only. So this is also SOP function. It's represented as level 1 is AND gates and then level 2 is OR gate. So multiple product terms are feeding into the OR gate. But the title here is I want to convert this to NOR only synthesis. Let us start simple. And I will add the bubbles in blue here. Let's focus on the OR gate first. How do I convert OR to NOR? Well, I have to add a bubble there and a NOT gate there. So because I added one bubble, I added another bubble on the same wire. And I did that because now this guy is NOR, and I can express this as that. A NOR gate in which both the inputs are tied together. So I'm done with that side. How about the ANDs? Well, you know that to convert a AND function to a NOR function, you need to add bubbles at the input side. Okay, so you add bubbles. How many? 1, 2, 3, 4, 5. 5 bubbles. Can you add just one bubble on those wires? No, you have got to add NOT gates here. So I have added 5 corresponding NOT gates in front. 3 input NOR gate, 2 input NOR gate. And each of these 5 inverters can be represented as this. So it's going to be a little bit of a messier circuit diagram, but you have essentially converted things to NOR only. Now, the other side of the story is going to be for product of sum functions. For product of sum functions, NOR will be very easy because it will be very similar to how we had SOP, easy conversion for SOP for NAND. The POS will be easier for NOR. And then you will have to play a similar game just as the slide shown over here for POS for NAND. What I mean by that is this. Let's see. Add another slide here. Right, this is POS now because you are doing the OR first and then you are ANDing them later. So if you wanted to convert this to say NOR only, it's going to be very straightforward because all you have to do is add, and done. Because as you can see here, this is NOR, and this is also NOR. For POS, NOR will be very, very simple. But if you were to convert to NAND, it is going to be a little bit difficult. So let me do this. NAND only. This is POS. What do you do here? NAND, NAND. Invert, invert, invert. Not, not, not. Not, not. Bubble, bubble. So each NOT has to be expressed as that. So you use this for each of these 5 as well as for this guy right here. And then the others are NAND, 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 and NAND. This is going to be a 3-input NAND. This is going to be a 2-input NAND. That's it. All right, let's see. For NAND only, if all the inputs are flipped for this diagram, is that possible to transform it into NAND? For NAND only, if all the inputs are flipped for this diagram, is that possible to transform it into NAND? Yeah, so if all the inputs are flipped, I hope you're talking about this possibility, right? If all the inputs are flipped, then essentially that NOT and that will cancel out. So you don't even need the 5 inverters in that case. Oh, for the first diagram. Okay, so let's see. Let's see. For the first diagram, NAND only. This is NOR only, NOR only, NAND only. Okay. So let's see. Your question is, Michael, if you instead of typing it in, do you mind using your mic and asking the question? It might go easier.
Yeah, so I mean for the first diagram, like we got 2 AND gates for the level 1 and OR gate for level 2. So if
Yes.
all the 5 inputs are flipped for the level 1, then how should we transform it into NAND only?
So if you are saying that if they are not gates here, right?
Yeah,
So if they are not gates over here, you would add these guys, 5 of them, over here, over here, over here, over here. So that's why I added this guy. I did this example just for that reason. Does that make sense?
uh, but,
So
uh,
here, let's see.
but what about the AND gate?
Let me give me 1 second here. What about the? What do you mean? So
Uh,
your question is, if all these are inverted, right?
yeah,
If all these are inverted and these are AND gates, this
yeah,
essentially looks like that. But this one is equivalent to NOR.
or
It is not equivalent to NAND. So if I want to convert to NAND, then I have to put a bubble in front, cancel it out, and for each of these guys, I have to represent using a NAND gate with both inputs connected together.
okay,
Like just
all right.
just as we did over here, right? You see, when A had a inverter in front, we represent that inverter, the NOT gate, using this.
Mm-hmm.
So even if you have 5 of them here, you would do 5 of those.
Yeah. All right, that makes sense.
All right.
All right, thank you.
No problem. All right. So we talked about SOP, POS, NAND only, NOR only, all the 4 combinations, and I hope that discussion was helpful for you guys. Now let us try to answer one more question that is outstanding. which is the CMOS question. Okay, so for that, what I'll do is I'll quickly, no, how do I do this? Sure, let's do it this way. So if I go and take a look at my midterm 1 resources, Spring, where is it? Right. Sure. Yes. Right. Now this question was, all right, so here, I think the confusion is this. The first thing that I want you guys to notice with a CMOS circuit is this. The entire pull down network that I'm going to highlight over here in green, say, this is the pull down network. The entire pull down network and the entire pull up network are complementary. You see, A and B are in series here. A and B are in parallel there. C, D, E are in parallel there. C, D, E are in series here. F is in parallel with all of that. F is in series with all of that. G is in series with all of that. G is in parallel to all of that. So everything is complementary with respect to the pull down and pull up network. So you could write the logic expression for X using pull down network, or you could do it using the pull up network. It doesn't really matter. Now, let's talk about the simplest CMOS network. What was that? NOT gate, right? So if you go in with say blue, I'll draw the blue. If you see this, if X goes in to the base of the NMOS or the gate terminal of the NMOS, you get X complement. This is the CMOS NOT gate. So you essentially are saying whatever input goes into the pull down network, invert it, right? Similarly, if you focus on this, what is happening here? For these two, what will you say? A and B. Is in parallel with C and D and E. That is in series with F. That is in parallel with G. But because this is the pull down network, you have to complement all of that, which is essentially your second form here. Or you could just focus on the pull up network. What is happening in the pull up network? You see, X goes in, it becomes a complement, and X complement comes out. A goes in, it becomes A complement. So you would write A complement or B complement ANDed with C complement or D complement or E complement ANDed with G complement. Oh, sorry, you would have to do what did I miss there? Oh yeah, or this or with F complement and with G complement, right? So that's the based on pull up network you get that, based on pull down network you get the second one. So you can use either one of the schemes to do it. You will get the same equation. These two are exactly the same. How do you know that? Well, apply De Morgan's law on this, you get that. All right, so questions here. I think all right, so what I'll do is this. I will stop the recording here.